Look at a type of problem that's called related rates. So let's just talk about this for a minute. Couple things. First of all, these problems with related rates are basically going to be story problems. Now, I know many students don't like story problems, but I want you to not get too worried because I don't think these are going to be horribly difficult as story problems go. Another key thing I want you to think about is this word rate, related rates. The word rate has the connotation of time, and really for us, the connotation is how things are changing in time. So in a minute, I'm going to, my first example is a very straightforward kind of problem. Now you notice I'm going to write down a formula that we all learned in geometry. If you have a circle with the radius, in geometry we learned the area of a circle is pi r squared. Pi, remember, is just a number. Matter of fact, just to make sure no one's confused about this, because we're going to talk about variables and stuff, I'm going to say the area is 3.14 times r squared. So it looks like we have two variables here. The variable a, which stands for the area, and the variable r, which stands for the radius of the circle. Now we call this kind of equation, this is a word you'll sometimes see in math and science, it's like a static equation. It's not changing. This is like a point in time. If I said, if r equals 3 inches, what does a equal? Well, you put in 3 for r, I'm actually going to use my calculator for this since I've got the 3.14. 28.3 square inches. So nothing is changing with respect to time. It just is what it is. However, now here is a different kind of problem. It's still a circle. We're talking about the area. We're talking about the radius. But now we're going to say a circle is continuously getting larger. And the way it's getting larger is this radius keeps growing. The radius is growing at a rate of 2 inches per hour. So that means if you wait an hour, the radius will have gotten 2 inches larger. So here's the question. when the radius is at 10 inches, what is the rate that the area is increasing? So in other words, now we have a problem where things are changing. This radius is continually getting larger, and obviously as the radius gets getting larger, the circle gets bigger and the circle grows. So here is how fast that radius is growing, 2 inches per hour. So they say, hey, when the radius reaches 10 inches, it's still growing, but at that point, right at that point with 10 inches, what's the rate that the area is increasing? All right, this may not make a lot of sense right now, but here's the whole key to how to do these related rate problems. First of all, related rate problems are, you take some equation like this, and in a sense we're going to factor in the time element, because now we have a situation where things are not staying the same, they're changing. And the way we account for how things are changing is, here's the whole key to these problems. You take the derivative of both sides of the equation with respect to time, or we think of the variable t. That's the whole key to solving these related rate problems, and because you do the same thing every time, knowing what to do is not difficult. Now the execution, if the equation's a little messy and you have to do some math, okay, you have to be careful, but knowing what to do is not that hard. And all these problems are pretty much the same. You're going to be given some kind of formula for some situation in nature, in medicine, in finance, in business, some kind of equation with multiple variables, and what's going to happen is things are changing with respect to time. They're not staying the same. Things are changing, and they're going to ask you some questions about how things are changing. And the way you're going to answer the questions is you're going to take the derivative of both sides of the equation with respect to time. And just to let you know, almost all the time, or for every problem, the time is not one of your variables you start with. For instance, this problem, there's no variable t. I have A for area and R for radius. But now here's a situation where, here's my problem. All of a sudden, the radius is changing, therefore the area is growing, and here's the question they ask. When the radius is at 10 inches, what is the rate that the area is increasing? What I'm going to do is, I'm going to take this equation, and I'm going to take the derivative of both sides with respect to time. So let's do that, and once we do that, then it'll be very clear what the next steps are. So I'm going to take the equation I was given, A equals 3.14 R squared. I'm going to take the derivative of both sides with respect to time. For related rate problems, it's always the derivative with respect to time, which is this small t here. Now it becomes an implicit differentiation problem. I'm taking derivative of the variable a with respect to the variable t. Since they're not the same, I take the derivative of a, normal derivative rules, which is just 1, but since a and t are different, you multiply by dA dt. Then over here, the 3.14 just comes out front. Now I'm taking the derivative of r squared with respect to t. Since these variables are different, I go ahead and take the derivative of the r squared, which is 2r, but then on the end, I have to multiply by dr dt. Now at this point is where you're able to go back and then look at your problem. I would not even try and move things around and solve this equation, because most of these variables here end up being replaced by numbers. So for instance, let's look at what we have here. What is dA dt? dA dt in words, if you look at the top, the area, and on the bottom is time. Therefore, this is how the area is either increasing or decreasing. Whereas the area is changing with respect to time. It's like area is on the top and time is on the bottom. Over here, we just have the radius of the circle at that point in time. But here's another dr dt. So what does this mean? This means how the radius is either increasing or decreasing. So you notice these two, dA dt and dr dt, are rates. It's volume per time. dr dt is like length per time. And we have an r here. So let's look back at our little problem and see what they tell us. A circle is continuously getting larger. The radius is growing at a rate of 2 inches per hour. Look at what that says. The radius is growing at a rate of 2 inches per hour. You know what this means? That's dr dt. It's how fast the radius is growing with respect to time. So if I go over here, let me just write it down. dr dt is 2 inches per hour. I'll go back to my problem. When the radius is at 10 inches. So they tell me, hey, let's go look at the situation where right now the radius is at 10 inches. Well, that means that I can set r equal to 10. So in other words, I'm looking at how things are changing at a specific point in time. This circle is growing continuously, but as soon as the radius gets to 10 inches, it's like I'm going to take a picture or a snapshot or stop and just see what's going on at this precise moment in time. So when the radius is at 10 inches, what is the rate that the area is increasing? Well, the rate they're increasing is, the area is A, and the rate it's increasing is dA dt, and that's what we're trying to determine. So from the problem, they've given us a number for dr dt, they've given us a number for r, and they're asking us to solve or to figure out dA dt. And I look at my equation up here. Let's simplify this by writing over here dA dt equals 3.114 times 2, 6.28 times r times dr dt. So I'm trying to figure out dA dt. 6.28 times r. I'm saying r is 10 inches. Times the r dt, which says what's the rate that the radius is changing. And it's growing, so it's a positive number, 2 inches per hour. So 2 inches per hour. So if I multiply this out, that's going to equal the rate that the area is changing. So 6.28 times 10 times 2. 125.6 square inches per hour. So at that point in time, the area is increasing by 125.6 square inches per hour. So that is a related rate problem. Let's summarize it again. We have an equation or formula. They give us some information initially. What I'm going to do is I'm going to take the derivative of this equation with respect to time. And by the time you finish that, you end up with this equation, dA dt equals 6.28 times r times the r dt. And then you take what information they've given you, and when you do, then we have a way to solve for dA dt. All right. So if I had to summarize it quickly, you're given a formula. Things are going to be changing. You take the derivative of the formula equation with respect to time. And after you take the derivative, then you go in and see what they've told you, and they're going to give you all the information you need except for what you're trying to solve. As a matter of fact, I have a book here to teach us story problems. Let me pop this up here. Let me try and make it so you can see this book. And we'll try to work this problem. I want to look at number 37. Maybe I'll even zoom it some. Suppose that the price P, so P is the price, how something costs, in dollars, and the number of cells X of a mechanical pencil are related by, so here's an equation. In this case, I have two variables. P, so we're talking about these mechanical pencils. P is how much the pencil cost, and X is how many of the pencils they sell. And they've come up with an equation that relates the cost of the pencil to how many they sell. And this is it. And then they say if P and X are both functions of time measured in days, so now they're saying these two variables, P and X, are changing all the time. Find the rate at which X is changing when... And then they give you this information here. So this is once again a snapshot in time. The snapshot in time is when X is 3. X is the number of mechanical pencils. P is the price in dollars, so it's $5. And look at here, dP dt is saying this is a rate. This is how P is changing with time. P is the price. So how is the price changing with time? It's 1.5. That means it's growing by 1.5. And what they're asking you for, they're asking for the rate at which X is changing. So really what they want to solve for is the X dt. So now let me go ahead and move this book and copy it on this equation and then talk through how we would solve this. Once again, this is a related rate problem. And in this case, they've given us an equation with some variables. And what I'm going to do is I'm going to take the derivative of both sides of the equation with respect to time. And then once I do that, I'm hoping I'll have everything I need to solve the problem. So let's write out this equation. 5p plus 4x plus 2px equals 60. So P is the price of the pencil in dollars, and X is the number of pencils sold. So basically, they're saying they have this equation that tells you how P and X are related. Basically, it's saying, hey, the price we try and sell the pencils at and the number of pencils we sell are related by this equation. But of course, now what's happening is they want to see how this information changes with respect to time. So here's what they do. Here is what I call the snapshot. Things are changing, but here's one point in time. They take a picture and we do a deep dive and analyze it. At this snapshot in time, they're saying at this point in time, we sold 3 pencils. And the pencils were $5 for each pencil. And then they say the PDT equals 1.5, and that should be in dollars per they measure it in days, dollar per day. So basically they're saying, how is the number of pencils changing with respect to time? It's growing. So each day that passes, the price of the pencil increases by $1.5. And the question is, find the rate in which x is changing. The rate at which x is changing is the x dt. So what I'm going to do now is I'm going to take this equation that has nothing to do with time, but however I know this equation is going to be changing, I'm going to take the derivative of both sides with respect to time. Let me just rewrite this equation. And that's what you do in related rate problems. When things are increasing or growing or shrinking, you're always going to take the derivative of both sides of the equation with respect to time. And you notice my variable, time, is not involved in the equation at all. So when I go take the derivative of this equation, everything's going to have the extra factor multiplied on, because there's no t's in my original equation. So for instance, derivative of 5p is going to be 5 dp dt. The derivative of 4x is 4 dx dt. Now this was a little trickier because I'm taking the derivative of p times x. I've got two variables multiplied together. I'm going to have to use the quotient rule. Quotient rule says the first times the derivative of the second plus the second times the derivative of the first. Now on the right hand side, derivative of 6 is just 0. Now the nice thing is, there are problems like this, normally you don't have to simplify and factor. At this point, I think it's easiest just to go plug in your numbers, because what's going to happen is they should give you the numbers for all these different variables or terms except for one. And the only one they don't give you is the one you're going to have to solve for. So what have they given me? They've given me x, they've given me p, and dp dt. So if I start plugging in things in this equation, 5 times dp dt was $1.5 per day, plus 4 times dx dt. That's actually what I want to determine. So I just rewrite that. Plus 2 times p, which is $5, times dx dt, which is once again what I'm trying to solve for. Plus x dp dt. X is 3 pencils. dp dt is how the price is changing. The price is changing $1.5 per day. So if I do some math, 5 times 1.5, I believe is 7.5. Plus 4 times the x dt, plus 10 times the x dt, and then 2 times 3, which is 6, 6 times 1.5. What do I have here? Oh, x times the PDT. Sorry. Sure, that was a little confusing. So 3 times 1.5 is 4.5. So now, 7.5 plus 4.5 is 12. Move to the other side. 4 dx dt plus 10 is 14 times dx dt. So if I'm solving for dx dt, minus 12 over 14, which is actually 6/7, but I think they probably want just a nice number, which is not too nice. 0.86. Now let me look, because I have the answer here and I don't see it. So this is typical. You may have seen my math error. Let me trace it back here, make sure I wrote the equation out correctly. Derivative of both sides, 5 dp dt plus 4 dx dt. Product rule, 2 times p dx dt plus x dp dt. So 5 times the p dt, 1.5, 4 times the x dt, we don't know that. 2 times 5, because p is 5, so that's 10. Times dx dt. I bet here's my mistake. 3 times 1.5, which is 4.5 times 2. See how it is? So this is actually 16.5. Now let's see if that looks more like, I have the correct answer here, so that's why I can check to see. And that's correct. Negative 1.18. pencils per day. Now what does it mean if this is a negative number here? that means, a negative number means something is decreasing. So dx dt is how many pencils are they selling per day? And at this point in time, actually, they're selling fewer pencils. So actually that's not good, because they're saying, I assume their goal is to sell as many pencils as possible. And the way things are going right now, the number of pencils they're selling is actually decreasing. All right, let's see if we have time for another couple of these related rate problems. Let me see the possibilities. How about, all right, let's do this one. I'll just read it here because it's not too complicated. It says the volume of a cantaloupe. So now it's like you're going to the store and buying some fruit. The volume of the cantaloupe is approximated by, now here's the equation, and this is actually the equation for the volume of a sphere. A sphere, you know, is like a ball. So they're assuming a cantaloupe is perfectly round, and the volume is 4/3 pi times r cubed, where pi once again is 3.14, a number. So r is like the radius. So like we have, right? So the radius is from the center of the sphere to the outside, and the volume is how big, you know, I keep using the word ball. It's also called a sphere. In this case, it's a piece of fruit, antelope. So the volume of the fruit is going to be 4/3 pi times the radius cubed. Now, I guess this cantaloupe maybe is still in the garden, so it's still growing. So it's not, I shouldn't have said it's at the store. It's actually still maybe in the garden. It's still growing on the vine. Matter of fact, the radius is growing at a rate of 0.7 centimeters per week. The radius is growing at a rate of 0.7 centimeters per week at a time when the radius is 7.5 centimeters. How fast is the volume changing? So here, before I even start looking at all those numbers in detail, I know what's going on is things are changing. The volume's increasing, the radius is increasing. So in order to be able to learn about this cantaloupe, I need to take and change this equation to a rate equation, which means I'm going to take the derivative of both sides with respect to time. Once again, time is not one of the original variables, so therefore every time I go take the derivative, I have to remember my explicit differentiation rules. So for instance, the derivative of v, since v is different than t, this ends up being dv dt. 4/3 pi, those are just variables, I can pull those out. The derivative of r cubed with respect to time, you do the normal derivative rules, but then you have to multiply when you're all done by dr dt. I can simplify this 3 and this 3. So 4 pi r squared. So the rate the volume is changing is equal to 4 pi times the radius at that point in time times the rate at which the radius is changing. Now I go back and say, what do they give me? They told me the radius is growing at the rate of 0.7 centimeters per week. That's dr dt. Okay, some of you, just to be very clear, let me put this up here. This is number Oh boy. Sorry. These machines lose their minds. So 47, the environment cantaloupe, so here's the equation. The radius is growing at a rate of 0.7 centimeters per week at a time when the radius is 7.5 centimeters. How fast is the volume changing at that moment? So the rate that the radius is growing is 0.7 centimeters per week, and the actual radius is 7.5 centimeters. So that's the information I was trying to write down. We took the original equation, and we took the derivative. It's right here. So they say the radius is changing at 0.7 centimeters per week. They say the radius at the time we're looking at is 7.5 centimeters. And they want to know how fast is the volume growing. So once again, simply plug in the numbers I have. I'm solving for dV dt. 4 times pi, which is like 3.14, times r squared, 7.5 squared, times the r dt, which I said is 0.7 centimeters per week. Now grab your calculator. 7.5 squared times 3.14 times 4 times 0.7, and it looks like dV dt is 494.6 cubic centimeters per week. All right, hopefully now you're seeing that these aren't that difficult. They usually give you the equation. You simply take the derivative of both sides of the equation with respect to time. And once you do that, then you go back and reread the problem and figure out all the information they've given you. And almost always, they're going to give you everything but one variable or one derivative, which you're then going to solve. Maybe I have time for one more. Let's see which one I want to do. Let's just do this one. This is sort of like a biology, medicine kind of problem. 41. Body surface area. Certain chemotherapy dosages depend upon a patient's surface area, sort of like how much skin they have. According to the Mosteller model, S equals square root of HW over 60, where H is the patient's height in centimeters, W is the patient's weight in kilograms, and S is the approximation of the patient's surface area in square meters. Assume that Kim's height is a constant, 165 centimeters, but she is losing weight. If she loses 2 kilograms per month, how fast is her surface area decreasing at the instant she weighs 70 kilograms? So let's, before we read too much into the problem, since they've given us an equation, a lot of times you can just take that equation and take the derivative of both sides with respect to time, and then once you do that, then you can go back and figure out what's going on. So let me write down the original equation. And usually when I write this equation down, I'll make little notes of what each of the variables represents. Now I know when I do this later on, I'm not going to leave a square root of, whoops. I'm not going to leave the square root in here. So actually, it looks like this, where S is the surface area of the person's body, H is the height of the patient, W is the weight. So they have this little equation that says if we know the height of the patient and the weight, we can figure out the surface area. But the point is, things don't stay the same. Things are changing. Because of that, we need to take the derivative of this equation with respect to time. Take derivative of both sides. You know what I'm going to do? I'm going to bring the 60 out front. So it's derivative of h to the 1/2, w to the 1/2. Left-hand side's easy. ds dt, 1/60 is out front. But now here I've got product rule. So let's write the first one, h to the 1/2, derivative of the second one, 1/2 w to the negative 1/2, but then dw dt, then the other half of the product rule, the second term times the derivative of the first term, and there's also a dh dt. Now this is looking very messy, but the good thing is very quick I'm just going to start plugging in numbers. So I'm not really going to try and simplify too much. I just want to clean things up a little bit so I can plug in the numbers. So 1/60. And actually I'm going to go ahead and get rid of I'm going to switch back to square roots because when I go to my calculator, I can do square roots. So this is like square root of h, that goes in the bottom, square root of w. I also have a 2 in the bottom here, times dw dt, how the weights change with respect to time, plus square root of w over 2 square root of h times the h dt. At this point now I go back to my problem statement and see what information they've given me. So they say, assume that Kim's height is a constant 165 centimeters. You know what that means? Her height. And because it's a constant, you know I have this dh dt, you know what that means? If something's constant, that means dh dt is 0. It's not changing. But she is losing weight, and if she loses 2 kilograms per month. So her weight, the rate at which she's losing weight is dw dt. And because she's losing, I have to make this number a negative 2 kilograms per month. So she's losing weight. It's how fast is her surface area decreasing. So they're really asking to solve for ds dt. How fast is her surface area decreasing at the instant she weighs 70 kilograms. So look here. First of all, dh dt is 0. This whole term goes to 0. And I know h, I know w, I know dw dt. Let me see if I can fit in the calculation here. ds dt equals 1 over 60. H is 165 square root over 2 square root of 70 times dw dt. In other words, how is her weight changing? Well, it says it's dropping by 2 grams per month. So it's -2. Now, I can just grab my calculator and let my calculator do all the hard work. 165 square root divided by 2 divided by 70. Oops, hit the wrong button. 165 square root divided by 2 divided by 70 square root minus 2 divided by 60 . So I got an answer of -0.0205 . I also want to make sure about my calculation. Once again, these problems can be not hard, but just a lot of stuff going on. So here's this product rule. 1/2 times the dw dt plus the h dt. Square root of h over 2 square root of w times the w dt plus, this whole thing goes to 0 because h dt. And then 1 over 60 times square root of 165 divided by 2 times square root of 70 times a -2. Let me do my calculation again just to confirm. Okay, 165 square root divided by 70 square root divided by 120 times, oh yeah, I think I made a little calculation error. This is what the book has. I was close, but I think I just made a little math error. So sorry about that. But the method's correct, just have to make sure I get the numbers down. Alright, so that's related rates. Hopefully not that hard once you do a couple. Once again, a lot of times they give you the equation. You simply take derivative of both sides with respect to time. Once you do that, then you go back to the problem and look at the information I've given you, and usually you can plug in all the numbers.